Yes.
Okay.
Yes.
Awesome. Okay. So today I'm going to talk you about pyTEAL, which is a different way to write Algorand smart contracts instead of writing just TEAL as Cosimo introduced you last time. And later during the session, Stefano will talk you about more recent way to handle like smart contracts and more advanced stuff. And then in the end, Chris will also present you another recent development in making even easier to write smart contracts for Algorand. If at any point you have any question, please use the Q&A and I'll try to answer as soon as possible. Apparently, I cannot see the chat, so please don't use that. Yeah, so we can start. So first of all, if you remember last time, Cosimo told you about TEAL, which is the Algorand virtual machine programming language. And this like this almost assembly-like language, which is used to run the Algorand virtual machine, which is a stack-based machine. And here we want to introduce you like a higher level abstraction on top of it in order to write code in an easier way. In particular, this is pyTEAL. So pyTEAL is a pattern language binding in the sense that is almost a tool to write smart contract codes. And when we are going to mostly talk about smart contracts, but the same thing can be used to develop smart signatures or logic sig. It's just that usually we use that for smart contracts, so I'm going to mostly talk about smart contracts. And that is that, if you remember, we have the Algorand blockchain, which is where the actual smart contract like reside and run. And what the code that specifies the behavior of the smart contract is written in TEAL bytecode, which is the thing that we need to specify in the transaction when we want to create a smart contract. To get this pyTEAL bytecode, we start from a TEAL source code, which is the usual TEAL that you saw last time. And this is compiled or rather assembled into bytecode using the Algorand SDK or in general an Algorand node. And today we're gonna see again a higher level abstraction, which is these pyTEAL expressions, which is a way to write this TEAL source code. So first of all, why we are doing this? The main thing is that TEAL is meant to be executed. It's not meant to be almost written, neither reasoned upon. So if you see a TEAL source code, it's very hard to keep track about what is happening. You need to remember how the stack is organized, what you're pushing or popping. In general, it's very hard to get an idea about what is actually happening. While with pyTEAL, we can write almost the same code, but in a way more concise way, in a way more readable way. And we are able to actually reason upon what is actually happening. So even for like auditing purposes or everything, it's way better than just writing for TEAL. Just as a side note, there are big projects on Algorand that are built using writing actual TEAL code, for example, Tinyman, but it's not the norm. Usually you try to use a better abstraction. And also, just as a side note, pyTEAL is one, maybe the most used way to generate the TEAL code, but there are also other projects like Reach or even other more ad hoc projects to get TEAL code from a different layer. So first of all, so what is pyTEAL? As I said previously, pyTEAL is a tool in some sense that lets you write Python code that generates TEAL code. So the idea is that we're going to write something, in this case, let's say the logic for a smart contract, and this is going to be compiled into TEAL source. So the general scaffolding will be something like that. So we have a program, which is a pyTEAL expression, and we're gonna see in the next slide what does that mean. And then we will be able to compile this expression into a TEAL source code in the sense that we are literally getting the TEAL code. Now, once we have the TEAL code, we can compile it into bytecode, and then we can use it to deploy our smart contract. Just to get an idea about what are actually expressions, but note that you need to be able to reason about what is happening, but you don't have to actually understand exactly how this works, but it's useful to avoid certain type of mistakes. So in pyTEAL, we create expressions, and an expression is an AST, so an abstract syntax tree, which is just a tree of the different operations inside that expression. So for example, we have a program like this, and in the next slide, we will see exactly what does that mean. But for example, we have a program that is a sequence operation. First, we have a for, and then we have an approve. So the pyTEAL expression at the root is going to be this sequence block, this sequence expression that will contain a for expression and an approve, which is the one at the end here. And then the for itself is going to have the different parameters, so the start, the stop criteria, and the increment, plus the actual body of the for. So this is just to say that we're working with expressions, and under the hood, there are those expression trees that we need to know that they exist, because we always write expressions, and in the end, our program is going to be like the root of an expression. So this means that there are going to be a couple of caveats that we need to be careful about. So just to begin, I'm going to refer to what Cosimo said last time about the internal of the AVM, but ideally, you should be able to write pyTEAL code without actually understanding how the AVM works and what's the need then. So first of all, remember that in the AVM, we only have two types. The first is the unsigned int, and the other is the byte strings. Here in pyTEAL, we have the same two basic types. So we can define, for example, that I is an int type, with the sense that is an unsigned int of 64 bits. And that's the value 5, or we can define byte strings. So for example, just plain like strings, but also we are not limited to like value UTF-8. So we can also have like random byte strings, or we can have like different encoding for those byte strings. And of course, given those two base types, we can perform some operation to go from one to the other. And again, those two are the only types that pyTEAL supports in some sense. Of course, this is very limiting. So later with Stefano, you will see how actually you can, in some sense, leverage those basic types to get more like complex types that helps to have more, to achieve more without having to deal with ad hoc encoding or similar. But for now, assume that you only have integers and byte strings. And of course, those are still the same limitations that the original AVM-based types have. So for example, the integer is a uint 64, so you cannot have negatives or greater than 64-bit integers, and byte strings as well have some limited capacity. Now, of course, the most basic thing that you can do, assuming you're working with integers, for example, is to perform math and Boolean logic operations. First, note that we said that we only have integers and strings, byte strings. So when we say logic operation, we mean that we work on integers with the usual, if it's 0, it's false, if it's not 0, it's true. So for example, if you see the last expression, k equal and etc., here we are performing Boolean operations, but the result is going to be an integer, either 0 or 1. Now, as we said previously, you can define integers variables. For example, by the expressions. So like I is 10. And then you can define expressions to compute something. For example, we can say we can perform standard math operations like multiplication, addition, subtraction, division, and like the whole bunch. But with the usual caveats that those are expressions. So J is going to be an expression that is an add because we have the same the standard precedence order. So it's going to be an add of a mul, so multiplication of E, which is again an expression. So this I is going to be int 10, and so on and so forth. So what does that mean is that, for example, if you want to compute something more, let's say, convoluted, let's say the square value of J, you can write Z equal J times J, but here you're actually repeating the same expression. So this is not going to be optimized in any way. So your Z value is going to be an expression which is a multiplication of a first instance of J and a second instance of J. So this clearly doesn't scale very well. So if you want to compute complicated stuff, you need to save intermediate results somewhere. And again, if you just say that J is equal to something, that is not doing that. It's just computing the expression. Now, of course, as with the integers, another thing that we can manipulate in terms of basic types is byte strings. And so we can do the usual concatenation, substrings, extract some slice within a byte string and similar, get the length. And one important thing here, as we saw previously, is that even if we have like constant value, we always have to wrap it in a pyTEAL type. So if we want to say the substring of y starting from index 2 up until the end of the string, we still have to specify 2 as a pyTEAL type. If we try to use like a simple q, like a Python type q, pyTEAL is going to complain about it. That's because under the hood, if you remember, the AVM is a stack-based machine. So if you say int 2, you actually need to push this value of 2 on the stack. So if you just say 2, it's not clear how to handle it. So you always have to use like pyTEAL types, even if are constants. And trust me, you're gonna forget it, and pyTEAL is gonna complain about it, and it's gonna happen a lot. Another set like of let's say useful operation, and again, I'm just going to give you an idea about what type of things we can handle in pyTEAL, is some standard crypto functions. So we can compute hashes. In recent versions of AVM, we can compute, we can verify signatures, and we will be able to verify, for example, state proofs and things like that. Now, again, when we say like, yes, these are expression and will be executed, but when we say will be executed, we mean that we're going to issue a contract call, so a transaction to a smart contract that will execute our code. So in order to get like the context of this execution, we have the ability to access basically the transaction that has caused our program to run. So for example, we can check who is the sender of the transaction, or we can check if it's an atomic group, what are our index within this transaction group. And also we can access the foreign arrays. Again, the foreign arrays, just as a refresher, are all the resources that our smart contract will interact with, and we need to specify it when we make the call to the smart contract. So for example, if you want to specify that we will interact with a different Algorand account, we need to add it to the accounts array when we do the transaction, and we can get this account from the smart contract side, checking the accounts array, for example. And of course, the same is true for application arguments. So if we want to supply, for example, assume we have a smart contract that just perform some math operations, we can supply the arguments to those math operations by using the application args array. As I said, we can have both like single transaction and group of transactions. So it's possible that we, in order to do some operations, we need to check if we are inside a group and, for example, just accept if, let's say, we have a payment transaction following us in the same atomic group. So we can also access those other transactions within a group. Not that you cannot access any other transaction. So either you can only access like your own transaction and the other within the atomic group. And so you can say, for example, let's check that the transaction before me. So my index is group index, -1 is the previous one in the group. And I'm going to check the sender for whatever reason, maybe want to check that is a specific account. And we can check that the type of transaction is a payment, for example, and the amount, and things like that. One thing interesting here, for example, is that if you see, we can both access the other transaction, but specify either like a pyTEAL expression, for example, tick_send.group index minus int1, but we can also do like 0 or 1 using just Python integers. This is normal, and this is because like under the hood there are different AVM opcodes that can work either with like stack values or immediates. So that is that pyTEAL here is hiding the complexity or routing the right opcode to output in the TEAL code, but presenting the same interface. So global like group transaction, tick_send accounts, and similar are some of the objects where you can access like a specific item by using both expression and pyTEAL integers. And finally, still talking about the context of the execution. Note that you can also access things like asking what is the size of the atomic group or what is the current number in terms of rounds. So for example, you can have some logic that triggers that is valid only if executed after a specific round number to fix like some temporal markers. Or you can also access like latest timestamp. One thing about it is that the timestamp is the block timestamp, but the guarantees on that are kind of weak. So like based on the type of application that you want to develop, you should be careful about leveraging latest timestamp, because if there are partitions or slowdown in the network, this could vary from like the real timestamp, or could also like not increment and stay the same for a series of rounds. So just be careful about that. So almost done. Like important, let's say, primitive that we can use is a log. So this is first of all very useful for let's say debugging purposes, and that is that we can log arbitrary bytes to the chain. So if we issue some logs, then we can inspect the transaction on an explorer or from the command line, and we can see exactly what were the logged values. An important thing about log is that is the only let's say direct way that the smart contract has to output something, because it could like issue a different transaction or write in the local state that we'll see shortly. But this is the only like direct way to output something, and in particular is the way that it is used when a smart contract call needs to return something to the caller. So now let's talk about the state. And again, here that is just to give you a broad overview about what type of operations we can do in pyTEAL. And you will see that we have this bunch of, let's say, operations or primitives, and we can actually write quite complicated code using just those. So the idea is that once you have an idea about what type of things is possible to do, then you can check like specific how to use, let's say, global put or similar to write what you need. So in terms of state, if you remember, we have two different states to persist data. The first one is the global state, and the other is the local state. So those are just like a key value storage type of thing that the smart contract can access. Global is the same storage for like all the, let's say, lifetime with the smart contract. So you can add values or change the values associated to a specific key, or delete the key if you don't need it anymore. And you can do that with this like app.global_put get and del. So for example, you can say, let's set the status to active. So this will write the key status with the value active. We can get back that value, for example, in a different call, and we can delete the key if we don't need it anymore. Two things about it is that first, when we create the smart contract, we need to pre-allocate in some sense, or like declare how many keys we're going to use at most. And if you try to use more keys, then the transaction will fail. That's why we also have this delete key operation. And another important thing is that like Algorand is a public chain and everything is public. So if you save something in the global state, like everyone from the Explorer can see what you have saved. And moreover, other smart contracts can see, like can access at execution time your global state, assuming that the right resources are defined when issuing the smart contract call. So differently from let's say Ethereum, for example, you don't have this secrecy in some sense, but you can access everything. One small caveat about this is that again, related to this, we are writing expressions, we're not executing anything. So if you recall, like ideally, in the end, our program is going to be just the root of an expression, because we're going to compile that, it's going to generate the TEAL, and then we can like assemble it and get the smart contract deployed. So for example, if you would like to do something like get the previous status, update it, and then do some actions based on the previous status. If we try to do something like this, so we define all status equal to the global get, and then our program is first we update it with a global put, then we check if all status is different from frozen, and if so, we do something. Let's say we log some bytes. Here, like we will never pass the if, in the sense that all status is always an expression. So this is going to be replaced with the expression global get. So even if we define it before it, doesn't matter. This is just going to be replaced as an expression. So this will always happen after the global put. So it's not gonna be what you may think. So just be careful about this, that you're only writing this expression. We'll see how to actually store temporary values in the next slides. The other type of state that I was mentioning before is the local state. So the idea again is that you have this global state where you can put up to 64 different keys. But if you are deploying an application that will need to interact with an arbitrary number of users, and for each user, you may want to save some information. Of course, you cannot do that using just the global state. And so you will need to use the local state. And here, the idea behind is the same as the global state. The only difference is that you need to define on which account, so whom global state you want, local state, sorry, you want to edit. And a couple of things about it. So first is that local state for a specific application and a specific user exists, so you can access it only if that user has opted in for that application. So if you want to call a smart contract that doesn't need your local state, you can just call it, you don't need to opt in. But if you need to interact with a smart contract, then it's to work on your local state for its application, like for that specific application. Then you need first to opt in to that application. And again, we have the same kind of interface. We can put stuff, we can get stuff, and we can delete keys. Okay. Now, in terms of, we already saw some control flow structures before, and just to recap them in a more like structured way. So first of all, if you recall, the like EVM accept or reject logic is that if at the end there is something on the stack and is a single value and is not zero, then is accepted. Otherwise, the transaction is rejected. In pyTEAL, we can directly say approve or reject to immediately exit and either approve or reject the transaction. So those are like exit from the program with either positive or negative status. Then, of course, since our program is a single expression, like the root of an expression, we need a way to concatenate multiple expressions together. And so we can use the sequence operation to say, for example, let's first put increment the count. So we say global put of count, and as value, we put the global get of count +1. So we're just incrementing it. And then we say approve. So again, this is like usually this is the basic block that is going to be used every time you need to do multiple operations. Now, as we briefly see before, you can also perform like comparison, and you can branch based on the result of those comparisons. And so you have these if, then, else, and also if, let's say, operations. So for example, you can say, if you can check if this count has reached a specific value, and then define two different branches that will happen if the condition was satisfied or not. And so, for example, you can say if the count is 100, then we can put in the key like 100th caller, the sender of the transaction. Otherwise, we just save that who is the last non-100th caller. And then we can increment our counter. So this is just, again, a sequence of operation. One is the if, and here we can define the condition, then the different branches. Another kind of like switch type of control flow that we can use is this cond. This was like this snippet here is something that was very like frequent previously when there was no like ABI support in pyTEAL and similar, and was the preferred way to define like the entry point of the program, to define the different actions that the program, different branches in some sense that the program may take based on what type of transaction was being issued. And the idea is that this switch, this cond operation, basically get a series of condition and an expression to execute if that condition is true. So for example, we can check if the application ID is 0, which means that we are just creating the application, and then execute the onCreate expression. And similarly for the other type of cases. Not that this is not used so much now that we have ABI support, and later on Stefano will show you how to do it in a more like in a cleaner way with recent developments. Also note that cond fails if there are no conditions met at the end. So for example, you could say that you just support some type of operations, otherwise you fail. And finally, you can perform like repetitions using for and while. So again, you can just define, if we see for the for, you can define what is the usual like starting expression, what is the check for branching out, what is the increment expression, the step expression. and then we have the body. Not that within the do, we can use only a single expression. So if you want to do multiple things within the for, you need to use another sec block. One thing about this is that, as we said, if we were to use just, let's say, e equal int of 0, and then say e less than 16, e equal e plus 1, for example, that will not work because I is just an expression, so that will not change at all during the execution. So we need a way to save temporary values. And to do that, we can use these scratch variables. If you remember, in the AVM, other than the stack, we have this scratch space, which is a place where we can put up to 256 values. And it's just a contiguous array, so we just need to have an index. But like all this is kind of hidden in pyTEAL. You can just say, I want I to be a scratch variable of type integer. And then you can say, for example, at the beginning of the for, store into I the value 0. Then the condition is check what is the value of I. So load from the scratch space the value of I and compare it to the some constant. And then for the step expression, we can say now update it. So store in the scratch variable the value of the scratch variable plus 1. So the scratch variables are the way to actually get some temporary results within our expression. So kind of finally, we're going to talk about like functions and particularly what are called like subroutines in pyTEAL. So assume for a moment that we are not using the subroutine decorator. And if you don't know what that is, like it's just something to change the function. So assume for a moment that the subroutine is not there. If we were to use just is even as it is, and we try to do, for example, global put of is even of 10, this will work, kind of as you would imagine. But the thing is that when we are calling is even, we are getting back the body of the function, which is an expression. So this means that if we were to call is even in different types, in different places in our program, each time we call is even, we will get like the whole body of the function inserted again. So if we call 3 times is even, we will have 3 different places where the whole body of the function is going to be present. And that's because, again, if we ignore for a moment the subroutine, we are returning an expression, and that expression every time is going to return, let's say, a different expression, a different object, and that is going to be put in different places. So in order to avoid this, we can use this subroutine decorator and just define once the isEven function, and then each time we call it, instead of getting the whole body, we'll just get a single TEAL operation that will perform the call sub of code in order to actually call the function, and then handle like passing the arguments and returning the values. This is especially important both if you have like functions with very large bodies, because you could very easily hit the limit of like source code dimension. Because if you remember in TEAL, you have like a limited space for the assemble TEAL web for the smart contract. So if you start to have like a lot of repetition inside your code, you will hit that limit very fast. And another thing is that if you try to have recursive functions, which are allowed, and you forget the subroutine decorator, basically what would happen is that the program will fail to compile, because each time we'll try to like actually recurse without any stopping condition in order to get the whole expression. And so Python will hit the stack overflow limit, and so you will not be able to actually compile this function. So always remember that if we have something that is not a very simple expression, so for example, in this is-even case, you could also say, okay, I don't want to have a subroutine because there is a small overhead. If it's just a single operation, I could live with just repeating the operation every time. But if you start to have more like bigger functions or recursive function, you have to remember the subroutine decorator. Also remember that each smart contract has also like an associated Algorand account. So you can send funds to the smart contract, or you can let the smart contract hold like assets or similar. And so you can also check what is the application address, which is, as a side note, like deterministically derived by the application ID. So you can also, given an application ID, you can also derive the address. It's not anything fancy. Another interesting thing that you can do with this, given that an Algorand Smart Contract has also an account, is that you can issue transactions within the smart contract. So what are called like inner transactions. So you can say, for example, you have a smart contract, you can call it, and if some conditions are met, the smart contract will pay a different account, an SQ, or pay you back, for example. And we can do that by using this inner transaction builder. And interestingly, we don't have like a big limitation on inner transactions. In particular, we can issue up to 256 inner transactions within a group. And also we can issue transaction to other smart contracts. So I have what is called like contract-to-contract calls in order to, for example, modularize logic within different smart contracts and have like a smart contract act as a provider of some information that you can query for from within a smart contract. So this helps to basically scale the range of what type of things you can do a lot. The only caveat is that, first of all, if you send a transaction to an Algorand account that is not the sender, you need to specify it before calling the smart contract. The same is true if you want to call a different smart contract, you need to specify in the foreign address before calling your smart contract that the smart contract you are calling will call a different smart contract. So this always because like in order to guarantee that the transaction can be executed very fast, there is this constraint that you need to define beforehand what type of resources you will need. And also another important thing to remember is that you can call like basically whatever you want, assuming that you specified it the right in the right resource in that foreign array. But the big limitation is that you cannot have reentrancy. So you cannot call yourself neither directly or indirectly. So for example, if you try to call a smart contract and the smart contract will try to call you back, this will not be allowed. This because like reentrancy was it's complicated to get it right because you are in this state where the smart contract starts to do something, maybe it's in like a non-valid state or whatever meaning of state. Then you call someone else, and then that someone else call you back, and now you're in this not valid state, and that thing can happen, and actually happen in the sense that a lot of like big issues, for example, in Ethereum or similar chain where reentrancy is allowed, we got like very big hack or similar bugs because of this. So in Algorand, we just say that you cannot do reentrancy at all, just to play safe. And of course, as I was saying, you can issue whatever transaction you want. So you can, for example, have your own smart contract minting an asset. So for example, here we can see that we are building an inner transaction that is an asset config. So we are creating an asset. We specify like some parameters, who is the manager and stuff like that. And then we submit it. And now we have this new asset that has been created by the smart contract. And so the smart contract can act like a treasury or whatever. And now just to mention briefly that, again, this was just to give kind of an overview about what can be done in pyTEAL, but note that there are also like other functions. For example, we can perform like wide math operation. So when either we need to do an operation where intermediate results would exceed the 64-bit unsigned integer, or operations where we want actually to work with like 128-bit integers. So we have a way to around that. And moreover, we can check, for example, the balances of different accounts, what type of assets they have, so what type of like Algorand standard assets. And also we can inspect that same assets to get, for example, information about the supply and similar. We also have like some limited JSON parsing. We have like a lot of interesting operations that allows us to have like quite a lot of freedom in defining what we want to do. But of course, like each operation, like again, pyTEAL is just getting TEAL, so each operation has the equivalent cost that would have writing it in TEAL. So that same limitation applies here. So that kind of it. That's it about the like general overview for pyTEAL. So if you have any questions or comments or anything that wasn't clear, I guess like if you're not familiar with Python, it's kind of okay if you don't get all of it, but consider that pyTEAL is pretty easy to be used, even if you're not very familiar with Python. And also here we were only talking about how you can use pyTEAL to get some TEAL code. We are kind of ignoring how to get, for example, okay, assuming that I have my TEAL, now I want to deploy the smart contract with this TEAL, or I want to interact with a smart contract that is already on chain. So we're not looking at it right now. There will be some bits of it later, and I guess mostly will be done in the next like more hands-on session on Thursday, I guess.
Okay,
So
you can see we have questions on the Q&A. If any students has questions, please use the Q&A now.
So I'm not familiar with the create2 opcode, so if you can add like a one-liner about it, I may try to answer it. Also, another thing just to remember is that we are talking about like some logic inside the program and saving stuff into the global state or local state and similar things. But remember that if at some point we either reject or we have some like runtime error, for example, we get an overflow or a meta error, or I don't know, we try to spend money that we don't have, then the transaction will fail, will roll back, and all the changes of the state will also roll back. The same is true if we try to issue inner transactions, so that the like atomicity kind of model will stay the same. So predict the alters where a contract will be deployed. So we cannot predict it. So what we can do is that we can issue we can create the smart contract with an inner transaction, and then we can access the resulting created ID. So for example, let me go back here. If you see here, this is the case for the standard asset for the asset, but the same is true for also if we try to create a different smart contract. After we issue the transaction, we can check what is the ID of the thing that we just created. So in some sense, we cannot predict, but we can actually create it and then do something with the resulting ID. I don't know if that answers your question. Otherwise, feel free to write it. Then a question for the log statement. Is representing the operation stack. So let's say that there are a couple of points here. So one is that each of those operations, let me go back to the log. Each of those operations are just like, in some sense, are an abstraction. So behind the hood, what pyTEAL will produce is that given the expression, the abstract syntax tree, it will kind of lay flat the different blocks, where each block is going to be like an operation. And it also includes like pushing things on stack and popping it from the stack. So for example, if when you say bytes of message here, you're actually pushing on the stack implicitly you're pushing on the stack a byte variable, a byte, let's say, content with message. So then when you call log, like the producer TEAL will just have these push bytes and then this log of code. So basically log is just like log, similar to add or almost all operation, will expect that you have some values on the stack before, and then when you invoke that specific opcode, it will check the top of the stack for the arguments. But the cool thing again about pyTEAL is that basically you don't have to think about it. You can just say log some bytes, or log what I get from calling up global get, or log from what I load from a Scratch variable, and that will work. Under the hood, each of those operations will involve one or more push or pop from the stack, invocation of different opcodes, and similar. Is there any idea suggested to develop in pyTEAL? So, okay, so this may be like a subjective thing. So pyTEAL is just a Python library. Basically, you can just install it with pip and just import and use it. What I've seen using, like what I've seen be used is Visual Studio Code and something else. I don't remember the other one. But there is a slide at the end. If we forget it, remember me and I will show you. Because like in terms of IDE, doesn't really matter, but there are some plugins for some IDEs that can help you a little bit. But in general, like is not like you can use basically anything that works with Python. You're just writing Python code. Next question. Oh wait, let me do this. Just okay. Next, contact as a deposit function, which can ask for as a deposit account until. Okay, yeah, it's only so. So assuming that you just want to have this for. I'm talking about the question about a deposit function which asks for a standard an asset. So this can be assuming that the standard asset is just like a general asset, is not like, for example, a managed asset where you have like clawback and things like that. If it's just like some random asset, what you can do is that you can have like a group transaction where you first have the smart contract call, for example, in order to let the smart contract knows that it has to perform like the opt-in to the asset plus some, let's say, some logic, and then within the same group you would have the like asset transfer call, and in this way, in the smart contract, you can have the logic to check if I'm within a group and I'm the first transaction, and the transaction after me is an asset transfer transaction, and asset ID matches and stuff like that. Now, all those checks, like some of those checks can be avoided if, for example, is not a general asset, but it's actually, let's say, a smart asset that, for example, the smart contract controls. So in that case, the smart contract could just issue a clawback operation on the asset and in some sense clawback from the user in order to get it without the user having to do basically anything other than just calling the smart contract. Yeah, and another thing is that these like for example, the order in which you want the transaction within a group, for example, may be important because let's say that you want to transfer, you say, I first transfer the asset and then I call the smart contract, but the smart contract may not have been opted in to that asset, then the first transaction will fail because it will be executed first. So just, yes, you can go away with you can get it working with group transactions, but you need to be like careful about the order. And another thing is that there are some standards that Stefano will talk about related to assuming that I want to call a smart contract and I want to have as an argument a transaction. So of course you cannot have like a transaction itself in some sense as an argument, but there is like a standard to specify how we can say that we want to do that and how to interpret those type of like more rich application calls. Curious to show about the reason why reentrancy smart contract calls are problematic. Okay, one thing, for example, is assume that, for example, assume that you're doing, let's see. So you could say that, for example, I have a flash loan application, and then I can let's see. Yeah, assume that you have the same application that handles both, let's say, loans, so flash loans, and governance. So the idea is that you could say, give me a flash loan, and then I can use .money to perform some governance operation on the pool of the flash loan app. And that, for example, could be problematic because then I could do something that I should not be able to do because those funds are not really mine, but are the funds of the same smart contract that I'm operating on. So trigger some sort of a change of state and then give back the flash loan. Now this kind of is not very like a neat example, but the general idea is when basically you assume that you have some invariance within the state of your smart contract that you need to make it invalid before you make it valid again. So the fact that you may issue a different call when you have this invalid state, and then that call could get back to you while you are in this invalid state will make it very, like, it may be possible to perform action that you was not supposed to perform. Now, I can check if you have like more, maybe later, I can give you some more specific pointers about this, but there were a lot of like hacks related to this, because again, the risk is that you are called when you are in a temporary state, which is not valid for what the smart contract is supposed to do. What do you think about the rich language? So rich is another way to basically produce TEAL, but the nice thing is that it's not limited to TEAL. So that is that you can write some code, and then you can get it in some sense compiled to different for different blockchains. So this means that you need to have a trade-off between like what you can support and what the like underlying architecture can support, because you want to have something that is kind of general. So it's very cool that you can write the same code and have it portable in some sense on different chain. But on the other hand, you cannot really leverage like the specific, let's say, powerful feature that Algorand or like a specific chain could have. But honestly, I'm not very familiar with it, so there it may be worth to give it like a look, even just to get an idea about again different ways to get TEAL. But yeah, it's definitely an alternative.
Okay, perhaps a final question from me about reach. Even if you don't know the specific of the language, it would be interesting to know the impact of reach on the developing of contracts for Algorand. How many contracts how many live contracts are developed in reach compared to the TEAL pyTEAL part?
So the answer is that I am not sure. I'm sorry, but just to clarify, I think that Rich is still going to produce TEAL code. So the architecture, like the underlying code, is still going to be TEAL. The only difference is how you get this TEAL code. So it can be pyTEAL, so Python based, or can be Rich, or can be other like ad hoc things. But yeah, sorry, I don't have. I'm not sure actually. I don't have any example of like a big project that was like developed using Rich. Also, like pyTEAL is useful because it integrates very well with the Python Algorand SDK. So we didn't see anything, but it is that you can have kind of the same in the same code, both the part that generates the smart contract, so the pyTEAL expression, then you can compile it and then you can deploy it, so create the actual smart contract with that code, all within Python, and it plays very well, like going from pyTEAL, so the generation part, to the Python Algorand SDK, so integration part. I guess we can have similar results using Rich and the JavaScript or TypeScript SDK, but I think that the best, like the best SDK currently is the Python one. So that may be another reason why pyTEAL is usually the preferred way.
Okay, thank you. So now there are no open questions. So I think we can have a break now. Like we can start at 20. So in 12 minutes, more or less. Okay, thank you.